morning. My name is Rachel Payton. This is team number 4. My teammates are Nate Brown, Ayad Al-Hurs, Bakr Al-Fardan, Murtada Al-Ahmad, and Ali Al-Rawan. And we're going to be describing to you our design for the pick-and-place robot. And you can see from the illustrations here that the side view and the top view, each of our subsystems are color-coded. You can get a basic understanding for our design. The subsystems that we have are the base in gray, rotary axes in red and green, grabber assembly, yellow, and our control systems micro switches are in blue. What we're going to be discussing today are the design specifications and calculations for each of the subsystems, as well as the materials that we're using, the speed and torque calculations and uncertainty analyses, as well as the electrical wiring. As you can see, overview here, we have an aluminum base as well as aluminum rods for the arms and the RP connections between each of the axes. Also, basics of the grabber, which will be a magnetic approach through a piston-based actuation device, and will all be controlled through an Arduino Uno and programmed through a laptop. So here is my teammate Nate with the base.
Thank you. Good morning. The base will be supporting the entire robot, also the Arduino board and all of the micro switches and balls. It features a housing to hold the lower stepper motor and pulley system, and also supports the Arduino board. We're making it out of aluminum alloy 2011, and it has 4 aluminum legs at the corners. We chose 2011 for its ease of machinability. Specifications, it's 27 centimeters by 25 centimeters. And we chose the thickness of 2 millimeters to bolster the strength a little bit. It will be 80 centimeters off the ground, and it'll weigh about 0.43 kilograms. For the deflection, we chose to do our calculations using a distributed load. We chose the distributed load because it has, while it has the rotary axis, it also has the steel ball, the weight of the steel ball spread out across the entire area of the base. So we figured distributed load would be the best. We used these calculations to find a maximum deflection of 0.38 millimeters. We also did calculations of a point load, which, and our answers of these same calculations came out to about the same deflection. For failure, we chose a safety factor of 5, and based on the Tresca failure criterion, our maximum shear stress was less than yield strength over 2 times the safety factor. So with safety factor 5, we found out that our base will not fail. Now here is Ed talking to you about the rotary axis.
Now I'll talk about the first rotary axis. The first rotary axis is attached to the base through a vertical support axis that is supported by a thrust bearing and a ball bearing. The first rotary axis has 5 components: a stepper motor, a drive pulley, a micro switch, a bolt, and a swing arm. Here's a cross section of the vertical support axis. As you see, here's the ball bearing that will support the force caused by the arm movement, and here's the thrust bearing, and that will support all the vertical load. Collars will be used to concentrate all the vertical load in the thrust bearing. The first rotary axis will be made from 2 aluminum rods, 147.5 in length and 5 millimeter in diameter. These rods are secured by 2 plastic plugs. The first one is attached to the vertical rotary axis, and the second one is attached to the second rotary axis. The first rotary axis calculations. These equations were used achieve 20 RPM in 0.1 second, which required a minimum torque of 0.012 Newton meter for the first stepper motor.
Go back to that. Why is there a 7-to-1 reduction in everything but the torque? It's a 7-to-1 gear ratio.
Yeah.
So why isn't it a 7-to-1 reduction in torque?
The torque for the arm was 0.089 and divided by 7.22, so we get 0.0.
I was looking at the available, okay. Got it, sorry.
Micro switches are used to set the home position for the rotary axis. The robot will return to the home position after completing the program. The first micro switch will be at the side of the base, in line with ball number 1. In line with ball number 4, I'm sorry. As you see here, here's that first micro switch. Will be with the first rotary axis. The second rotary axis is carried by the first rotary axis, and it supports the rubber assembly. The rotation is provided by a vertical shaft that is connected to the second stepper motor by a pulley system. The second rotary axis is exactly the same as the first one, except that its end is attached to the ground. The second rotary axis calculations are the same, except that the minimum torque is 0.0027 Newton meter for the second stepper motor. And the second micro switch is located at the side of the base, aligned with bulb number 1, as you see here in this picture. Here's exactly where it's at. Second micro switch. And now with my teammate Bakar with the rubber.
Okay, I'm going to talk to you about the reverse simply, which is in circle here. It's rule to pick the steel ball and release it through either hole A or hole B using servo motor. It has 4 components: servo motor, piston, and ring magnet, and the rubber housing. Here I show you an expanded view of the rubber. You see the servo motor and an aluminum piece which connects the servo motor to the piston. And you see here a ring magnet. You can see this picture in here. It has hole in it, so we can attach it to the piston using a screw. And here is the rubber housing. As you can see here, there are 2 holes in here to connect the rubber housing to the second rotary axis. And you see here a small hole. I'm going to put you further. The second hole, we're going to use it. We're going to insert an aluminum rod of 2 millimeter just to fix the second rotary axis to the rubber assembly. Fix it enough. And you might see in here, I don't know if you can see it. There's a ball housing of the diameter of 0.5 inches, just to fix the ball in it, so it may not slip off while moving the rotary axis. Here is our calculation for the minimum torque for the servo motor using this formula. For the force, we consider both the ball weight and the magnetic force, and we got a minimum torque of 0.152 Newton meter. And here is my teammate Murtala talking about the control.
Right now I'm going to talk about the control subsystem. The Arduino control board will be used to drive both rotary axes and the grabber assembly. We will use the laptop to provide the code that's sent through the Arduino board to control the rotation of the both of the stepper motors and the servo motor. The control subsystem has three components: Arduino with motor shield and a laptop which provides the coding and also the Arduino software. As you can see here from this diagram, wires will be used to connect each component to the Arduino board. Also, there will be one resistor for each micro switch, and the Arduino board will be connected to a power supply of 12 volts. This picture shows how are we going to connect the servo motor and the second stepper motor to the Arduino board. There will be a wire from the servo motor attached to the second rotary axis in 2 points. Here is the first point and here is the second point. Also, it will be attached to the first rotary axis in 2 fixed points, and there will be a hole in this gear which the wires can go through it into the Arduino board. For the first stepper motor and the micro switches, a wire will be a wire from the Arduino board along the base will be attached to it. Now is my teammate Ali will talk to you about the uncertainty analysis.
I will talk about uncertainty analysis. We use a various Taylor series expansion to calculate our uncertainty for both x and y direction. This gave us the density for each component from the 4 inputs, which are L1, the length for the first arm, L2, which is the length for second arm, theta 1, which is the angle between the first arm and the x-axis, and theta 2, which is the angle between the second arm and the first arm. Those are the equations that we use to calculate our uncertainty analysis in Microsoft Excel. The combined standard uncertainty analysis for whole A and both x and y directions was 1.63 millimeters on the x direction and 1.12 millimeters on the y direction, which is fairly enough for our design. And now we will be with my teammate Rachel to talk about the summary.
So in summary, and I have to apologize for a typo here. It's not, the base is not 6061, but rather 2011 aluminum alloy. But we specified to you our design measurements and calculations, the materials for each of the components, and the wire on the board. We also discussed the grabber assembly and the servo to control that, and the Arduino programming that will control both rotary axes through the stepper motors. We discussed the torque calculations and requirements for our desired speed, and we'll take any questions.
So in operation, are you planning on raising the spear that you're picking up over all the other spears or maneuvering around the other spears?
It's hovering.
Oh. So then your drop will be from more, about a half inch. Right, if you're gonna, because you don't have an extra degree of freedom, all you can do is drop your piston down and bring it up, and then it'll be released when you pull that piston through the hole, right? It'll just drop out. Okay.
Why do you have it standing 80 millimeters off the table?
So we have to have a minimum height up to have a cup underneath each of the holes to collect water.
That was, yeah, that was my.
Okay.
Let's see kind of a side view of the robot, speaking of height stuff. Yeah, all right, John, you want to ask your round? Just setting you up for John here.
So, these are tooth belts, right? Where's the adjustability to tension the belt?
I guess that could be determined by the actual setting of the rods into the plastic components. If we needed to play with them a little bit.
So you can't get them over the, you can't assemble the belt on there right now. You need to, I don't know how you're gonna put it together. The belts won't go over the
No, that picture was just
Oh.
fine. Let's go back to that picture. So axis number one, you've got this block here that's sitting on top of your thin plate, and it's got a pair of bearings in it. And then a shaft that sticks out above there. And the pulley is there, and so the tension of the pulley is trying to bend that rod. And then further up there, I have the arm that sticks out of there, and it's a big bending moment on that vertical rod. And that vertical rod of axis one is basically a cantilever that supports your entire robot. What's the deflection of that gonna be?
Don't have those exact numbers.
I'm afraid you're going to be very disappointed in the performance of that. The part of the reason that it all gets like this is that everything ends up so high because you put everything above the plate there. You might want to reconsider and put the motor and the pulley for axis one underneath the plate. And now everything drops down by several inches. You have better bearing support for your axis one, and it's a more elegant looking design. Is that what you're expecting me to ask about?
Something like that. Never done the torque on arm one question.
Now, why don't you take that one? Good.
Okay, so let's say arm one, we'll put everything in the vertical here so you can see what I'm doing. This is arm one, this is arm two at 90 degrees to arm one, here's your gripping mechanism, right? So if I have a force out here, both from self-loading and let's say the magnet force out there, it causes a moment about arm one, like this, right? With parallel rods that look like this, they aren't very stiff in torsion. And so another issue to consider is with this thing hanging out in this direction and wanting to pull down because torsion of arm one, how stiff is it going to be in torsion? And with the configuration you have right now, the answer is not very stiff. And plus the fact that those two aluminum rods, while they might be plenty strong going back to an RP base, and you put a torsion on that base, either it's excessive deflection or you crack your base. Something to think about as you proceed.
Do you think those forces are significant to actually potentially cause failure of the component?
I think you can do those calculations.
Similarly, look at the load path at the connection of your second axis to your first axis. And so how you transmit stability and take up that force load hanging off. How are all of the sprockets attached to their shafts? How are you transmitting torque through all of your sprockets and belts?
From the first arm to the second arm, from the second stepper motor to the second arm.
Shaft to gear. How are your gears attached to your shafts?
There will be a small screw in the pulley, like what we did in the air engine for the flywheel.
So you have set screws.
Yep.
Do you have flats on your shafts? Have you looked at the loads that you
No,
have
I
and
haven't.
your arms are swinging and you suddenly stop your motor? Are they okay?
We haven't done the flat for in the shaft.
Back on the base, I saw a safety factor for a direct shear load, but nothing manual. Did I miss that, or did you not do that calculation? That one right there. Is direct shear the largest load, largest stress?
Probably not.
Okay.
That's the only, okay, what we get.
So you'll check that axis, bending is probably bigger than that.
You guys heard that somewhere, I seem to remember. Where do we always fail? 9 times out of 10, when does it fail? Either bending or shear.
Unless it's really short, low profile, bending is gonna be the worst.
Rich didn't should have caught that, took my class.
And can you flip up one to the actual picture of the base plate? So that sort of top leg there with the narrowest support, and if that's got full moment load on it, that would be the weakest point, because that width there is much narrower than the rest of the plate. I don't know if you can see what I mean there, but
Yeah, if you came out here, ironically,